Section: Introduction. We're going to talk about a new approach to generative applications, such as creating images, videos, 3D models, audio, and text. These applications often use something called diffusion models, but there's a problem. When we want to create high-resolution content, these models struggle. They have to process the entire high-resolution input at each step, which is computationally expensive and memory-intensive. To overcome this, we often use complex deep learning architectures, but these can be difficult to optimize and still require a lot of computational power. Recent research has tried to make these models more efficient, but so far, the results haven't been great. The best we've managed is a resolution of 512 by 512 pixels, and even then, the quality isn't as good as other methods. Some approaches, like DAL-E2, Imagine, and eDiff-I, try to save computation by learning a low-resolution model first and then using multiple super-resolution diffusion models to enhance the resolution. However, these components are trained separately, which complicates the process and often requires careful tuning of parameters. In this paper, we introduce a new approach called Matryoshka Diffusion models, MDM. This is a new type of diffusion model designed for creating high-resolution content. The key idea is to include the low-resolution diffusion process as part of the high-resolution generation, similar to how multi-scale learning is used in generative adversarial networks, GANs. We achieve this by performing a joint diffusion process over multiple resolutions using a NestedUNet architecture. Our main findings are that MDM, combined with the NestedUNet's architecture, allows for a multi-resolution loss that greatly improves the speed of convergence of high-resolution input denoising. It also enables an efficient progressive training schedule, which starts by training a low-resolution diffusion model and gradually adds high-resolution inputs and outputs following a schedule. We found that this approach strikes a good balance between training cost and model quality. We tested MDM on class-conditional image generation and text-conditioned image and video generation. The results were promising. MDM allows us to train high-resolution models without resorting to cascaded or latent diffusion. We also found that both multi-resolution loss and progressive training greatly boost training efficiency and quality. Furthermore, MDM can generate high-quality text-to-image models with a resolution of up to 1024 by 1024 pixels, even when trained on a relatively small dataset. Finally, MDM can also be used for video generation, suggesting that our approach is versatile. Now, let's talk a bit more about diffusion models. These are a type of latent variable model that are trained with a denoising objective. Given a data point and a fixed signal noise schedule, we define a sequence of latent variables. The model then learns to reverse the process with a backward model, which can be rewritten as a denoising objective. This is often done using a neural network that maps a noisy input to its clean version, conditioned on the time step. However, this process can be challenging for high-resolution generation, especially for complex tasks like text-to-image synthesis. Some diffusion models use a cascaded approach, where a first diffusion model is used to generate data at lower resolution, and then a second diffusion model is used to generate a super-resolution version of the initial generation. However, each model is trained separately, which can limit the quality of the final output. Section summary. Diffusion models have become popular for generative applications, but scaling them to high resolution poses challenges due to the need to re-encode the entire input. In this paper, the authors propose Matryoshka diffusion models, MDM, that include a low-resolution diffusion process as part of high-resolution generation, resulting in improved training efficiency and quality for high-resolution synthesis. Section: Latent Diffusion, LDM, Rombach 2022 High. In contrast to other methods, latent diffusion and its subsequent developments manage the creation of high-resolution images by conducting diffusion in the lower-resolution latent space of a pre-trained autoencoder. This autoencoder is usually trained with adversarial objectives. However, this approach not only makes the learning process more complex but also limits the quality of the generated images due to the lossy compression process. Recently, several strategies have been proposed to train models directly on high-resolution space, without the need for separate models. These methods focus on designing efficient networks and adjusting the noise schedule to accommodate high-resolution spaces. However, these methods do not fully consider the inherent structure of hierarchical generation, which results in their outcomes falling behind cascaded and latent models. In this section, we introduce Matryoshka Diffusion models, MDM, a new type of diffusion model that is trained directly in high-resolution space while taking advantage of the hierarchical structure of data formation. MDM first expands standard diffusion models in the extended space, for which we propose specialized nested architectures and training procedures. Unlike cascaded or latent methods, MDM learns a single diffusion process with a hierarchical structure by introducing a multi-resolution diffusion process in an extended space. Given a data point, we define a time-dependent latent variable. This variable is similar to a posterior equation for each of its components, where a deterministic downsample operator depends on the data. This operator produces a coarse or lossy compressed version of the data point. For example, it can be an average pooling operation for generating low-resolution images. By default, we assume compression in a progressive manner such that the size of the data decreases as we move from one resolution to the next, with the original data being the largest. Also, there are resolution-specific noise schedules. In this paper, we adjust the noise schedule based on the input resolutions. MDM then learns the backward process with neural denoisers. Each variable depends on all resolutions at a given time step. During inference, MDM generates all resolutions in parallel. There is no dependency between the variables at a given time step. Modeling diffusion in the extended space has clear advantages. It enriches the complexity of the model distribution and opens up opportunities to share weights and computations across variables, enabling us to reallocate computation in a more efficient manner for both training and inference efficiency. Similar to typical diffusion models, we implement MDM in the style of UNet, using skip connections in parallel with a computation block to preserve fine-grained input information. The block consists of multi-level convolution and self-attention layers. In MDM, under the progressive compression assumption, it is natural that the computation for one variable is also beneficial for the next. This leads us to propose NestedUNet, an architecture that groups the latents of all resolutions in one denoising function as a nested structure, where low-resolution latents will be fed progressively along with standard downsampling. This multi-scale computation sharing greatly eases the learning for high-resolution generation. Aside from the simplicity aspect relative to other hierarchical approaches, NestedUNet also allows to allocate the computation in the most efficient manner. Our early exploration found that MDM achieved much better scalability when allocating most of the parameters and computation in the lowest resolution. Similar findings have also been shown in other studies. Section Summary. Matryoshka Diffusion models, MDM, are a new class of diffusion models that are trained end-to-end in high-resolution space, leveraging the hierarchical structure of data formation. Unlike cascaded or latent methods, MDM learns a single diffusion process with a multi-resolution dependency in an extended space, allowing for efficient computation allocation and improved scalability. The MDM architecture, called NestedUNet, groups the latents of all resolutions in one denoising function, enabling multi-scale computation sharing and facilitating high-resolution generation. Section: Learning. We teach our multidimensional model, MDM, using a standard denoising objective at multiple resolutions. This means we adjust the model's parameters to minimize the difference between the model's output and the actual data, at different levels of detail. We use a specific weighting for each resolution, and by default, we set the ratio of the weight at a given resolution to the weight at the highest resolution equal to the ratio of the number of data points at the highest resolution to the number of data points at the given resolution. We also use a progressive training technique, which has been shown to speed up the training process. This involves dividing the training into several phases, where we gradually include higher resolution data into the training objective. This is like learning a series of MDMs on a sequence of data points until we reach the final resolution. This method avoids the time-consuming process of training with high-resolution data from the start, and it speeds up the overall convergence. We can also mix different resolutions in the training, which involves training with samples of varying final resolutions within a single batch. MDM is a versatile technique that can be applied to any problem where the input data can be progressively compressed. We demonstrate its effectiveness with two applications beyond class conditional image generation: text-to-image and text-to-image video generation. In this paper, we focus on publicly available and easily reproducible datasets. For image generation, we used the ImageNet dataset at a resolution of 256 by 256 pixels, and the conceptual 12M dataset at both 256 by 256 and 1024 by 1024 pixels. For text-to-video generation, we used the WEBVID-10M dataset at a resolution of 16 by 256 by 256 pixels. We chose to use the conceptual 12M dataset extensively for text-to-image generative models, which is a significant departure from previous works that relied on large and sometimes inaccessible datasets. We found that the conceptual 12M dataset is sufficient for building high-quality text-to-image models with strong zero-shot capabilities in a relatively short training time. We evaluate our image generation models using the Frechet inception distance, FID, and clip scores. To examine their zero-shot capabilities, we also report the FID clip scores using the COCO validation set to generate images with the models trained on the conceptual 12M dataset. We implemented MDMs based on the NestedUNet architecture, with the innermost UNet resolution set to 64 by 64 pixels. We shifted most of the self-attention layers to the lower level, 16 by 16 pixels, features, resulting in a total of 450 million parameters for the inner UNet. The high-resolution part of the model can be easily attached on top of the previous level of the NestedUNet, with a minimal increase in the parameter count. For text-to-image and text-to-video models, we used the Flan T5XL as our text encoder due to its moderate size and performance for language encoding. We also applied two learnable self-attention layers over the text representation to enhance text-image alignment. For image generation tasks, we experimented with MDMs of different resolutions. For video generation, MDM is nested by the same image 64 by 64 UNet with additional attention layers for learning temporal dynamics. The overall resolution is 64 by 64, 16 by 64 by 64, and 16 by 256 by 256. We used bilinear interpolation for spatial resolution, and first frame indexing for temporal resolution. We applied progressive and mixed resolution training for all MDMs. We used 8A100 GPS for ImageNet, and 32A100 GPS for conceptual 12M and WEBVID-10M, respectively. Section Summary. The authors propose a multi-resolution denoising model, MDM, that can be trained using a normal denoising objective at multiple resolutions. They also introduce a progressive training technique that speeds up the training of high-resolution models by gradually adding higher resolutions to the training objective. The MDM approach is versatile and can be applied to various problems, such as text-to-image and text-to-video generation, and is evaluated using publicly available datasets. Section: Baseline Models. We've compared our multi-resolution diffusion models, MDMs, with three basic models to understand their performance better. 1. Simple Diffusion Model, DM. This model uses a standard UNet architecture, similar to recent end-to-end diffusion models, and applies it directly to high-resolution inputs. We also considered a NestedUNet architecture, but without considering the low-resolution losses. 2. Cascaded Diffusion Model, CDM. This model is directly comparable to MDM. It uses an UP sampler with the same configuration as our NestedUNet. We also added noise to the low-resolution conditioning image and adjusted the noise level during inference for optimal results. 3. Latent Diffusion Model, LDM. This model uses latent codes derived from autoencoders and trains diffusion models that match the dimensions of the MDM UNet. We compared these models on ImageNet with 256 by 256 resolution. For the simple DM, we used a standard UNet. For the cascaded DM, we trained a 64 by 64 diffusion model for 200,000 iterations and applied an UP sampler UNet of the same size. We also applied standard noise augmentation and adjusted the noise level during inference for optimal results. For the LDM, we used pre-trained autoencoders that downsample the input resolution. We used the same architecture for these experiments as our 64 by 64 low-resolution models. For the MDM variants, we used a NestedUNet of the same size as the baseline UNet. We experimented with two variants, one trained directly with the multi-resolution loss, and another one resuming from the 64 by 64 diffusion model, which we call progressive training. Comparing the simple DM to MDM, we found that MDM converges faster and performs better in the end. This suggests that the multi-resolution diffusion process and the multi-resolution loss effectively improve the model's convergence, with negligible added complexities. When we followed the progressive training schedule, MDM's performance and convergence speed further improved. Interestingly, the cascaded DM significantly underperformed MDM, even though both started from the same 64x64 model. This is remarkable because the cascaded DM has more combined parameters than MDM and uses twice as many inference steps. We believe that the inferior performance of cascaded DM is largely due to our 64x64 model not being aggressively trained, which causes a large gap between training and inference with respect to the conditioning inputs. Lastly, compared to LDM, MDM also shows better performance. Although LDM is more efficient due to its small input size, MDM features a simpler training and inference pipeline. We also compared MDM to existing approaches in literature and found that MDM provides comparable results. We also demonstrated MDM's strong zero-shot capabilities of generating high-resolution images and videos, despite training on relatively small datasets. We conducted ablation studies to understand the effects of progressive training and found that more low-resolution training clearly benefits the high-resolution FID curves. Training on low-resolution inputs is much more efficient in terms of both memory and time complexity, so progressive training provides a straightforward option for finding the best computational trade-offs during training. We also compared the performance of using different numbers of nested resolutions and found that increasing from 2 resolution levels to 3 consistently improves the model's convergence. Lastly, we showed that MDM is similarly amendable to classifier-free guidance, CFG, as other diffusion model variants. Despite being trained on a significantly smaller training set compared to other models, MDM still demonstrates a strong CLIP score. Section summary. The authors compare their multi-resolution diffusion models, MDMs, against 3 baseline models: simple DM, cascaded DM, and latent DM. They find that MDMs have faster convergence and better performance compared to simple DM, outperform cascaded DM despite having fewer parameters, and show better performance than latent DM. Additionally, MDMs provide comparable results to existing approaches in the literature and demonstrate strong zero-shot capabilities in generating high-resolution images and videos. The authors also conduct ablation studies, showing that progressive training and increasing the number of nested resolutions improve the model's convergence, and MDMs are amenable to classifier-free guidance. Section. Related work. In the field of image generation, various methods have been employed, including diffusion methods and multiscale models. One popular approach is the use of generative adversarial networks, GANs, such as the LAPGAN model. This model starts by creating low-resolution images using simpler models, which are then fed into more complex models to generate high-resolution images. Another approach is the use of autoregressive models, which have been used in a variety of applications, from early works like Pixel CNN and Pixel RNN to more recent text-to-image and text-to-video models. While earlier models often worked directly with pixels, recent models like Party and Make a Scene use autoencoders to convert images into discrete latent features. These features can then be modeled auto-regressively using large sequence-to-sequence models based on transformers. The FDM model proposed a generalized framework that allows for progressive signal transformation across multiple scales. It also introduced a denoising scheduler to transition between different resolution stages, a feature we have incorporated into our work. Similarly, the IHDM model performs end-to-end generation from coarse to fine by reversing the heat equation, implicitly increasing resolution. In our research, we demonstrated that training models on lower resolutions first and then sharing these representations across different resolutions can lead to faster training and high-quality results. We believe this is because the model can more effectively exploit correlations across different resolutions, both spatially and temporally. While we have only explored a limited number of architectures in this study, we believe that further improvements can be made by exploring more weight-sharing architectures and finding new ways to distribute parameters across different resolutions. A unique aspect of our work is the use of an augmented space where denoising is performed over multiple resolutions simultaneously. In this approach, resolution over time and space are treated the same way, with the differences in correlation structure in time and space being learned by different parameters of the weight-sharing model. We also propose a more general way of optimizing over multiple resolutions by decoupling the losses at different resolutions and weighting them differently. This could potentially allow for a smooth transition from training on lower to higher resolution. While we have compared our approach to the LDM model in this paper, we believe that these methods can complement each other. For instance, it is possible to build the MDM model on top of autoencoder codes. We would like to express our gratitude to Miguel Angel Bautista, Jason Ramapuram, Alaudin El Nubi, Laurent Din, Reixiang Zhang, Yuyang Wang for their insightful suggestions and valuable feedback on this project. We also thank Ronan Collibert, David Grangier and Ani Hannan for their invaluable support and contributions to the dataset pipeline.